Hi, my name is Ethan Fury One Sams, and I've created the space engine. Like a car engine goes in a car, or a boat engine goes in a boat, the space engine goes into a spacecraft, and not a spaceship, because space travel is not something that you get in a ship and go. It is a craft that takes a lot of consideration. And it's not the type of complicated consideration. It's just the craft that makes it work. So we're going to be talking about high and low energies in the universe, high and low energies in the celestial bodies that we're used to, and some physics that makes the space engine work. And without the physics laws that I'm about to introduce to you, the space engine would not work. And I have a third law that pertains to the stability of the space engine, because there's things that will make the spacecraft tumble, but I'm going to explain why that does not matter, and why you can overcome any challenge presented by the forward thrust of the non-propellant propulsion system, which is the space engine I've created. So without further ado, the first law, or Ethan's first law of Einstein's relativity: two forces may be relative to each other and may be manipulated to interact directly by transfer of energy to one another via mass, or acted upon from an outside force or mass in respect to their relativity. What's that? Well, that's something that we see here in our own cosmic neighborhood, the Milky Way. Obviously, there's something in the middle of the Milky Way. It's a mass or large gravitational pull, some black hole. We can't see it, but we know it's there, and we orbit around it. Well, we do. We orbit our sun, and the sun orbits the Milky Way, but the forces that cause us to orbit the sun and the moon to be tidally locked and orbiting the Earth, those forces together relative to each other orbit the Milky Way, and not the Milky Way itself here on Earth, or our moon. It's tidally locked to us and not them. And that is a reasons of that's why the space engine functions, because things work relatively in this manner, and that the forces and the configuration that they will be in the space engine will allow it to stay together and work. And so in the space engine, or let's talk about the energies, excuse me. So at the center of the Milky Way, you have a large mass that everything is orbiting around. That is our point of lowest energy. If you try to get out of the black hole, or out of the center of the Milky Way, you're going to have a hard time, because you're going to have to climb out of the lowest gravity well. And that's something the space engine can do. It can climb. That is the same reason why we haven't gotten to the moon with a manned mission, because the moon is at the top of the Earth's gravity well. Now, we can get to the moon, don't be mistaken. It's just not as easy as you would think. And it definitely wouldn't be the first place you would go. In fact, it is impossible to go straight from the Earth to the moon with a manned mission as it is now, because of the length of travel. What you would have to do is actually leave Earth, head off the planet the closest celestial body that you could actually stay at until you could get back to Earth's orbit in an allowable time window. There is very possible that you can leave Earth and head off Mars's orbit and get there, and then not be able to get back to Earth for another year. So until you could get back, then you wouldn't be able to actually stop at the moon first. That's just the way that space travel works. And I know maybe it's not good to hear from me, but it's the truth. So we'll move on to Ethan's second law of Einstein's relativity, mass has gravitational energy, and that would change the E equals mc squared to E equals m, open parentheses, the speed of light, c squared times the gravitational energy of that mass, close parentheses. So you can see the equation here. You can see mass twice on the same side of the equation, and you can see mass on one side of the equation twice, and then you can see energy on both sides of the equation. And what that really turns us into is it turns the equation into an open conduit, a free-flowing conduit, because the universe, in respect to these energies, means that either A, there's a big bang and everything started from a very low energy, or B, there was no big bang and it's actually we're in a free-flowing conduit where a point or something before us that is causing us to expand, and because there's expansion, there isn't that means the Big Bang theory would be impossible. We just don't know why we're expanding, but we know that we are expanding, and we know that it's going to be a point of high energy, something we would have to get to, because everything coming out of it is going down to a lower energy. So everything with the energy on both sides of the equation is a snapshot of time. So that's all we can really perceive. And so you can see when they do electrical noise experiments with plasma, and they start shocking things with electricity or energy, and they start seeing things kind of separate into different types of waves or different things that they can see. Well, they're just disrupting kinetic energy with noise. Everything is energy, is because everything is gravitational energy, and everything, the fabric of everything that makes up the universe, that we can see, is tied into that gravitational energy. And you can see that with our telescope, and when it saw the furthest thing that we've seen, the furthest galaxy that we've ever seen, and it was happening next to a black hole through the gravitational lensing thereof. And when we looked out there, we didn't see that black hole and see another telescope, and that telescope looked even further. Well, these are two different types of lenses, and the gravitational lens is the lens that just how a probe slingshots its way around a planet to go faster. It did the same thing with light. It accelerated those photons, the photonic force, and it shows that light just isn't energy. Light is interacting with gravitational energy. That means that there's a mass associated with it. So you would say that okay, well, it's a special type of mass that only works with gravity. And I can explain why it's a little bit different too, because we've measured that time slows in areas of high gravity. At least if that's true, and if that's true, and light travels through an area that bends the light and accelerates through slingshotting the photons, the photonic force, then it's obviously happening in an area of the type of gravity that will slow time. So there's an interaction there that is demonstrating the aforementioned point. And I'm just going to smile right now because with all this physics theory and 10 minutes in, it is really easy for me to lose track of what I'm talking about. But we know that light is not the cosmic speed limit, and that it's not necessarily having a mass interaction, but it's having an interaction with gravity that nothing else is really having interaction with. And I think that it kind of hints that because the speed of light is accelerated, it's not the speed limit. Obviously, there's things that travel faster than the speed of light. It's obvious. Any quasar or spinning black hole is going to tell you that. There's definitely things traveling faster than the speed of light. There's definitely gravitational energy that's, light cannot escape from. So so what that would mean is that, just because there's always in every propelled cycle in the space engine, you're going to be able to go faster, and it's going to be based on power. We're going to talk about the forces that propel you. So we know that centripetal force is mass times the velocity of the spin, which is dictated by the amount of power you apply to the rotation, and or what it is at the time, divided by how big the centrifuge is. So if you have a small centrifuge and you have enough power to get that mass moving and spinning, that's going to be an exponential increase in force. However much more power you have, you're going to exponential, and you can move that mass. The faster you get that mass going is exponential. So the more power you have is exponentially inclined for how much of a thrust you can get for a single point in time. So how much kinetic energy you can get in a single point in time is exponential. That's good, but that's not very. That's going to overcome gravity. But the thing is that gravity is a constant force that no matter how fast your processor is, there's always going to be a gravitational reading no matter what, because it's an infinite force that's moving at the speed of if there's anything that has a constant speed limit that you can't get past, it would probably be the speed that gravity actually pulls on you. And I don't believe a processor can even process that. I don't think that that even that's necessarily something that would be that's just existence right there. You can go 10 million times the speed of light and still be in existence. But maybe you get crushed in a black hole and you don't exist. I don't know. Maybe you go to another place where you're not existing. Okay. Well, let's say now that you see that you have an exponential increase in based on how fast you can get your counterweight moving around the centrifuge, and say you release it and it propels you forward, and you overcome gravity and you're moving forward on your gravity. If you're trying to defeat gravity, if you're in space, there's not going to be a counteraction to that. You're just going to propel, and you're going to, next time you do it, you're going to propel at that faster speed. And in space, what you're going to see is that the faster that the drivetrain works, that actually takes that counterweight and reintroduces it to the centrifuge and actually physically attaches it to it, which is why it's a spacecraft, because you actually have to craft a counterweight that will actually do that. And get ready to do your high school science project, because that's all you need is to levitate. I'm going to tell you right now, anybody can do it. You just have to understand the physics involved, and you could plug something into the wall and you craft you a centrifuge, and if it's light enough, you just plug it in the wall and have a power ratio that has overcome the force. And that's, you get the idea. You're gonna really need some good fissile material to really get this stuff off the ground. And whenever you're trying to get defeat gravity with a good amount of mass that's trying to move habitat into space at a point of high energy where we can actually force multiply our work in space and actually be a spacefaring civilization and build gigantic ships and really live the sci-fi imagination of what our future is. It's going to, we have to start small, and it's going to start with a single space engine or two, or whatever amount of space engines, and you have to get an asteroid and make a bigger space engine out of it, and a lot of things. It's going to do a lot of things for everybody on Earth, and you can tug an asteroid into geosynchronous orbit, and you can drop it to the Earth at terminal velocity simply by slowing it down and slowing it down and slowing it down, and you can drop an asteroid onto the Earth and have it not be much worse than a plane crash. That's just what space engine allows you to do, because you can climb a gravity well. That is I really think that's it. There's people that say, well, it's not going to work because of basic principles of motion. Well, let's say you're on this is not a two-dimensional, because you got two forces that are allowed to interact via force with Ethan's first law of Einstein's relativity. You're not bound to just a single action. You're not measuring a single thing. You got two different things going. You have a centrifuge. Okay, well, the centrifuge is working. Yes, you're going back and forth, but that's basically a circle giving you a linear, reading of how far forward or backward you are. Okay, but when you release it, it's got no respect to what your velocity is. Okay, you're just going back and forward faster and faster and faster, but the thing is, you're gaining energy. Okay. What is low? What's the difference between low and high energy whenever you're going around in a circle? There is no difference on that linear graph. You're not gonna, that's not going to make a difference. So when you release it and it propels you forward, well, when you release it, there's no reaction when you release it, because you're dropping it off the centrifugal cliff. Okay, when you drop something off a cliff, you don't get blowback that sends you flying up into the air as something drops onto the ground. It's just not how gravity works, because it's inverted gravity. It's just how it works. And when it gets to the end of the well of the craft, it propels the craft forward. And what happens after it propels it forward? Well, it doesn't bounce back. It's just the fact that the craft and the counterweight are moving at the same speed relative to each other at that point. So whenever you have your drivetrain that actually pushes it back, or pulls the counterweight back to the centrifuge, and you reattach it to the centrifuge, and you may even actually do it favorably to power to actually help you get back into that spin. Well, that's just another linear back and forth action that cancels each other out. So that's it. That's space engine. That's how you travel in space, and it's so easy to do. And you think about Oumuamua, the first interstellar object, and the fact that the trajectory it came in at, it left at almost the same trajectory it came in at. And the funny thing is that it wasn't moving very much faster than our probe. That's the farthest thing that we've sent out into space. And I just got done playing at Star Drive, and what I would do in Star Drive is I would have drones, and they would just go sit in the system, some random place in the system, and observe. There's nothing saying we can't observe very easily the same way that we detected Oumuamua. There's if you can observe things, activity, Oumuamua is something that we probably should get a space engine out there and make sure that we can tug it back in the next 300 or 400 years. I'm just saying that, and whatever it is, let future generations figure out what that is. But the fact that the space engine speed is so exponential that it may not actually take that long. But honestly, I'm gonna tell you right now, I don't think we're ever going to find that object. I don't think we're ever going to find a Muamua. And if we do, well, then it means it's not anything. But if we can't, well, we know something came through. Alright, well, this is Ethan, Fury 1 Sams. Make sure that you give me credit for the space engine, especially when you bring it to your high school science project or your science fair and you got something flying around and you had no idea that, there's people out there that create flying saucers. Or me, because I invented it and just explained it to you. Make sure you give me credit, because they're not going to write Ethan's law of Einstein's relativity in the books just because it's true. So thanks, guys, and let's think of a slogan real quick. It's not going to be a Buzz Lightyear. It's gonna be a have a good one. Bye now.